Some people chase the sun. Others, apparently, decide to build one from scratch. In a gleaming lab in Hefei, China, a group of scientists just pulled off something that sounds like it came straight out of a sci-fi movie. They made a mini-sun, an artificial one, and kept it running for over 1,000 seconds. That might not sound like much, but in the world of nuclear fusion, it's a huge feat. It also brings us closer to humanity's long-time dream of clean, limitless energy. So let's break down how this artificial sun actually works, why it's such a big deal, and what it might mean for your electric bill in the future. If you're into science that's finally catching up to science fiction, give this video a like to show your support, and let's get started. When scientists refer to China's artificial sun, they're not talking about a giant flashlight in the sky. This sci-fi sounding project is officially known as the Experimental Advanced Superconducting Tokamak, EAST for short. Located in Hefei, this machine doesn't glow or rise in the east each morning. But it does something arguably cooler. It replicates the sun's fusion process on Earth. Now, what exactly is fusion? In the simplest terms, it's the process where atoms smash together to form new ones, releasing enormous amounts of energy in the process. It's how the real sun powers the solar system, and how fusion promises to power humanity, if we can get it right. The catch is, you need to reach temperatures over 100 million degrees Celsius. That's hotter than the sun's core and definitely hotter than your air fryer can handle. Just this year, EAST held a steady-state, high-confinement plasma. You can think of it like an ultra-hot, swirling soup of charged particles maintained for a jaw-dropping 1,066 seconds. That's nearly 18 minutes of holding something hotter than the sun in a magnetic container. For comparison, the previous record was 403 seconds. Both records were set by the same machine. Clearly, this thing is competitive, even with itself. The scientists at the Hefei Institutes of Physical Science under the Chinese Academy of Sciences see this as a huge leap toward a real, working fusion power plant, one that could someday generate electricity without the radioactive waste of nuclear fission or the emissions of fossil fuels. As Songyun Tao, one of the lead researchers, put it, a fusion device must achieve stable operation at high efficiency for thousands of seconds. In other words, this 1,066-second milestone is just an early step toward making fusion energy usable. Before we get lost in magnetic fields and plasma pulses, it's worth asking, why are scientists around the world throwing billions of dollars, decades of effort, and a fair bit of sanity into building an artificial sun? The answer isn't just because it sounds cool, although let's be honest, it really does. It's because fusion energy could solve some of humanity's biggest problems in one fell swoop: climate change, energy scarcity, and the looming dread of running out of clean, reliable power. If you're looking for a scientific miracle, this is it. Right now, most of the world relies on fossil fuels like coal, oil, and natural gas. These are finite, dirty, and politically messy. They pump out carbon dioxide, which in turn makes the Earth hotter, the oceans angrier, and weather more unpredictable. Not exactly ideal for long-term survival. Then we have nuclear fission, which is cleaner than fossil fuels and very powerful, but it comes with its own baggage: waste, meltdowns, and a PR problem that no amount of cute uranium mascots could fix. Fusion, by contrast, is like the clean energy version of winning the lottery, except instead of one lucky ticket, everyone wins. The process involves fusing light atomic nuclei, typically isotopes of hydrogen like deuterium and tritium, into a heavier nucleus. This releases massive amounts of energy without the dangerous waste products that fission leaves behind. No long-term radiation, no carbon emissions. As for the fuel, deuterium can be extracted from seawater, and lithium, which can help produce tritium, is found in the Earth's crust. In other words, the raw materials are both abundant and geographically widespread. You don't have to invade a country to mine hydrogen, but of course there's a catch. Fusion is also hard. Very hard. While the sun pulls it off effortlessly thanks to its massive gravitational pressure, We Earthlings have to use machines like tokamaks to force atoms together using extreme heat and powerful magnetic fields. That's where EAST and its record-setting performance comes in. Keeping plasma stable at 100 million degrees Celsius, the temperature required for fusion, is like trying to balance Jell-O on a trampoline during an earthquake. The longer you can do it, the closer you get to making fusion practical. So when East held that super-hot plasma for 1,066 seconds, it was actual proof that humanity is inching closer to unlocking energy that could power cities for centuries with nothing more than water and a little lithium. The achievement builds on over 70 years of global fusion research, where each breakthrough has been hard-won and painstakingly validated. Unlike solar and wind energy, which are weather-dependent, or hydroelectric dams that need massive landscapes, fusion can, in theory, run 24/7 anywhere on Earth. But while this kind of progress brings us closer to real fusion power, it also reminds us just how crazy the conditions are behind the scenes. Here's the paradox that every fusion scientist lives with. To replicate the sun's power on Earth, you need temperatures higher than the sun's core, but you also need to not melt everything around it. The material challenge alone is enough to make most engineers cry into their blueprints. But the people behind East didn't flinch. They faced the beast head-on. How do you trap and control a blob of plasma hotter than 100 million degrees Celsius without turning your lab into a crater? First, let's talk about that heat. The fusion process demands such high temperatures because it needs to overcome the natural repulsion between atomic nuclei. Normally, atoms prefer to keep their distance, like introverts at a party. To get them to fuse, you need to slam them together with enough force to break through their mutual discomfort. That's where the extreme heat comes in. Heating the fuel until it becomes plasma, the fourth state of matter, where electrons and nuclei roam freely and bump into each other with enough energy to fuse. Now, how do you contain something so hot it makes lava look like bath water? That's where tokamaks like EAST come into play. Instead of trying to build a physical container that can handle those temperatures, spoiler, you can't, scientists use magnetic fields to hold the plasma in place, kind of like creating an invisible cage that floats the plasma in mid-air, never letting it touch the walls. The shape of this magnetic bottle resembles a donut, an extremely high-tech, highly unstable, spinning donut made of lightning. The East tokamak uses a combination of superconducting magnets and advanced confinement techniques to create this magnetic bottle. These magnets operate at cryogenic temperatures. Just to add contrast, some components are colder than deep space, while the plasma inches away is hotter than the sun. If that sounds absurd, it's because it is. Fusion labs are like nature-defying sandwich makers, ice cold on the outside, fiery chaos in the middle, and somehow it all works. But plasma doesn't just sit there politely once confined. It writhes, it shifts, it tries to escape. Maintaining it in a stable, high confinement mode called H mode in fusion speak is where East really shines. They were able to hold a stable high confinement plasma for 1,066 seconds without any disruptions. That's the longest anyone has ever managed to keep that kind of controlled insanity going. And what makes this even more impressive is the scale. The heating systems at East are absurdly powerful, comparable to 70,000 microwave ovens running at once. Without this much power, maintaining plasma long enough for research would be nearly impossible. But let's be real. When someone says their machine runs with the power of 70,000 microwaves, you expect popcorn. At East, you get plasma hotter than the sun. That's the scale we're working with here. And while this sounds like something a mad scientist would cook up in a villain's lair, it's actually one of the most carefully engineered and scientifically significant systems on the planet. The heart of fusion research is not just about reaching unimaginable heat, but also about keeping it going. That's where East's recent upgrades come in. After the record-breaking 403-second run in 2023, Chinese researchers knew they needed more power and more control, so they tuned up the machine like a race car headed for its next impossible lap. One of the most important systems they focused on was the heating mechanism, also known as the powerhouse behind the artificial sun. The previous configuration of East's heating system could already blast out energy at an absurd level, but now it's been nearly doubled. Think about that for a second. Doubling something that was already equal to 70,000 household microwaves is like saying, sure, the volcano is impressive, but can we make it 2 volcanoes? And they did, without destabilizing the whole experiment. The upgrades didn't just crank the heat either. They improved precision, consistency, and operational control. That's key. You don't want to just heat plasma. You want to heat it evenly in the right spots and sustain that heat without sending the system into chaos. The heating system now includes advanced neutral beam injection and radio frequency heating methods. In simple terms, it bombards the plasma with high-energy particles and electromagnetic waves to stir it up and keep it energetic. It's like giving the plasma a constant energy drink through a fire hose. According to Gong Xianzu, head of East's experimental operations, every tweak to the machine, from heating to magnetic shaping, has been about achieving stability. The kind of sustained confinement East pulled off for over 1,000 seconds didn't happen because someone hit a lucky button. It happened because the system was engineered, tuned, and battle-tested over years to deliver exactly this kind of performance. More importantly, all of these upgrades serve a larger purpose: feeding data and operational experience into future, full-scale fusion projects. East is essentially the world's most extreme beta test, laying the groundwork for reactors like the International Thermonuclear Experimental Reactor and China's future Fusion Engineering Test Reactor. The work being done in Hefei is forming the blueprint for what a commercial fusion plant might look like in the next couple of decades. It's also worth noting that East isn't doing all this by themselves. As an open testing platform, it regularly collaborates with global researchers, sharing insights and integrating new ideas. For a project that's literally trying to recreate the sun, it would be a bit ridiculous to think that just one country could do it alone anyway. Fusion is the kind of challenge that doesn't care about borders, politics, or whose turn it is to host the Olympics. It requires a level of international cooperation that makes space missions look simple. Fortunately, the race to master fusion has gradually evolved into something better than a race. It's become a joint mission. China, although relatively new to fusion research with the launch of East in 2006, quickly became one of the leading contributors to the field. That same year, China officially joined the International Thermonuclear Experimental Reactor Project as its 7th member. For context, ITER is the largest and most ambitious fusion energy project ever attempted. Built in southern France, ITER is where more than 30 nations have come together to construct the world's biggest magnetic confinement fusion reactor. It's fusion's version of the United Nations, except instead of speeches, they build plasma containment vessels the size of office buildings. China's involvement in ITER goes well beyond formality. Under the agreement, China is responsible for about 9% of ITER's construction and operational commitments. That's no small feat. The heavy lifting falls to ASIPP, the Institute of Plasma Physics, which also runs EAST. They've been developing critical components like superconducting magnets, diagnostic systems, and heating technology, all of which feed directly into the ITER build. East, in this sense, is a sandbox where China road tests what it plans to bring to the big leagues. But why does this collaboration matter so much? Because fusion is not like other energy systems. You need a convergence of ultra-high temperature physics, materials science, precision engineering, software control systems, and cryogenics, all operating perfectly together. No single nation has all the answers, but collectively, we might just have a shot. This isn't just China and Europe either. The United States, India, Japan, Russia, South Korea, and the EU are all in on ITER. Each brings something unique: materials expertise, funding, operational systems, or decades of research. It's a level of scientific diplomacy that feels refreshingly optimistic in a world otherwise full of tension. If you want a story where global powers actually work together for the common good, fusion energy is it. Building a sun in a bottle might be the hardest thing we've ever tried, but we're not doing it alone. We're doing it as a planet. East's achievements are especially important because they directly support ITER's roadmap. Every breakthrough in long-term plasma confinement, heating consistency, or magnetic stability informs design tweaks and risk assessments for ITER. The 1,066-second record, while it definitely grabbed attention, didn't power anything in your kitchen. Not yet, anyway. East is still considered an experimental reactor, which is the scientific way of saying it's not ready to power your home. But the progress being made is laying the groundwork for something very real. The first generation of fusion reactors that can actually produce usable electricity. And that changes everything. So how do we get from an experimental plasma playground to a fusion power plant humming quietly in the countryside? The short answer is slowly, but methodically. The first hurdle is turning net positive. Right now, East and even larger projects like ITER use more energy to run than they actually produce in fusion power. That sounds like a bad business model, and it is. But that's the nature of cutting-edge physics. East's mission isn't to break even on energy. Its goal is to prove that the physics works, that the plasma can be sustained, and that the materials can hold up under monstrous stress. It's like testing a rocket engine indoors before launching the real thing into orbit. The leap from test rig to commercial reactor is being handled by next-generation fusion machines, most notably the upcoming China Fusion Engineering Test Reactor. Unlike East, CFETR isn't just a science platform. It's designed with the ultimate goal of producing electricity. This is no easy feat. To pull it off, engineers need to crack several more technical challenges. One of the biggest is handling plasma material interaction. When your reactor core is hotter than the sun, every part of the machine has to be made from materials that can withstand insane temperatures, intense magnetic fields, and rapid neutron bombardment without falling apart or turning radioactive. There's a lot of research going into advanced metals, heat-resistant ceramics, and even liquid metal walls that can absorb the brunt of the punishment. Then there's the fuel cycle. Future reactors like CFETR or ITER will likely use a mix of deuterium and tritium, two hydrogen isotopes. Deuterium is easy to find, but tritium is rare and radioactive. So fusion engineers are designing systems to actually breed tritium within the reactor walls, using lithium blankets that produce tritium when bombarded with neutrons. It's like building a power plant that grows its own fuel. A weirdly self-sustaining concept that feels almost alive. And let's not forget the power conversion systems. Once a fusion reactor produces heat, that heat needs to be used to boil water, spin turbines, and generate electricity just like any other power plant. But because fusion conditions are so extreme, even the heat exchange systems need to be revolutionary. Conventional steam turbines may not cut it. We may need new kinds of energy capture tech that can keep up with the intensity. East, for its part, continues feeding all this critical data into the ecosystem. Every long plasma pulse teaches engineers something new. How to fine-tune the magnetic field, where the energy losses occur, what kinds of instabilities arise. While these aren't headline-grabbing discoveries, they're quite essential. Without them, CFETR and ITER would be flying blind. The jump from East's glowing blue donuts of plasma to the lights in your living room may still be years, maybe even decades away. But the steps are being taken, and slowly but surely, it's moving forward. Thanks for watching all the way through. If this topic kept you interested, we've got more in-depth videos on cutting-edge science and tech waiting for you. Stick around, explore the channel, and remember, understanding how the world works makes it a little more exciting to be part of it.